Hey everyone, and welcome back to The Explainer. I am so incredibly thrilled to have you here today because we're going to be decoding the invisible chemical world around us. We'll be looking at a truly foundational technique in chemical analysis, a process that's absolutely crucial to modern science, yet operates completely out of sight. Today, we're unpacking the general aspects of chromatography. So imagine you're handed a glass of what looks like perfectly clear water, or maybe a single drop of a really complex pharmaceutical compound. Here's the puzzle we have to solve. How do scientists actually separate the invisible, seemingly inseparable components of that mixture? I mean, when everything is blended perfectly into a single homogeneous liquid or gas, how do we pull out the individual building blocks to see exactly what's inside? Well, to understand just how vital solving that puzzle really is, let's think about this number, 50%. The sales of chromatographic instrumentation represent at least half of all global sales of analytical equipment and materials. Let that sink in for a second. Half! Out of all the analytical techniques out there, chromatography literally has the widest scope of applicability. It's a massive, absolute game changer of a tool that powers labs all across the globe. Our roadmap for this explainer is pretty straightforward. We'll cover 1. What is chromatography? 2. Mobile and stationary phases. 3. Classifying the techniques. 4. Key chromatographic methods. And finally, 5. Reading the chromatogram. Okay, let's dive into section 1. What is chromatography? At its core, chromatography is a physicochemical process. It belongs to a family of fractionation methods, kind of like distillation or crystallization, where the ultimate goal is separation. Now, to appreciate where we are today, we really have to look at how this evolved. The method, in its modern form anyway, originated at the turn of the century with the foundational work of Michael Tzwedt. And actually, we attribute the very terms chromatography and chromatographam directly to him. Now, for a long time, analytical chromatography was, well, pretty limited. But then, right around 1940, a major breakthrough happened. An optical device was placed at the end of a column, which meant scientists could suddenly identify the migration time of components without needing to physically collect them first. Fast forward to the modern era, and the development of highly sensitive detectors has allowed us to miniaturize the whole system. Today, we're analyzing incredibly tiny quantities, we're talking just a few nanograms here, with continuous detector registration. All right, moving right along to section 2, mobile and stationary phases. Every single chromatographic separation relies on a fundamental duality. On one side, we have the stationary phase. And just like the name implies, this phase is immobilized, usually packed right inside a column. On the exact opposite side, we have the mobile phase. This is your transport mechanism, usually a liquid or a gas that is actively flowing through the system. The whole principle of chromatography is based on the differential migration of your compounds of interest as they move through that column. Because different compounds interact differently with the stationary phase versus the mobile phase, they end up traveling at totally different speeds, which ultimately leads to their separation. And there's a mathematical backbone to this, defined by the Nernst distribution coefficient, or KD. It's simply the ratio of the solute's concentration in the stationary phase compared to its concentration in the mobile phase. What's super fascinating here is that these KD values can vary wildly depending on the physical nature of your phases. For instance, if your mobile phase is a gas and your stationary phase is a condensed state, your KD value can jump incredibly high, sometimes up to 1,000. This brings us to section 3. Classifying the techniques based on phase polarity. Because we can swap out whether our phases are liquids, solids, or gases, we end up creating entirely different analytical environments. It's brilliantly illustrated when you map out the pathways based on whether the phases are ionic, polar, or nonpolar. For example, matching an ionic stationary phase with an ionic mobile phase gives us ionic chromatography. But if you match a nonpolar stationary phase with a polar mobile phase, you get reversed phase liquid chromatography. Having this incredibly wide range of techniques is exactly what permits scientists to select the perfect, most suitable tool for their specific analytical problem. Now let's zoom in a bit for section 4, key chromatographic methods. Keeping that broad classification in mind, let's systematically break down the key combinations used in labs every single day. First up is liquid-solid chromatography. This is actually the earliest type of chromatography out there where the mobile phase is a liquid and the stationary phase is a solid. Next is liquid-liquid chromatography. Here, an inert support immobilizes a liquid stationary phase, and the separation process is based on the partition of the analyte right between the two liquid phases at their interface.
And finally, gas-liquid chromatography. The mobile phase here is a gas, and the liquid stationary phase is typically immobilized on the inner surface of capillary columns.
Now, liquid-solid chromatography is incredibly widely used, and it actually subdivides even further based on the exact retention phenomenon at play. Let's rapid fire through these. First, adsorption chromatography, where solutes bond to the stationary phase through physical or chemical interactions. Second, ion chromatography, where the stationary phase has modified ionic sites that exchange mobile counterions with ions in the sample. And third, molecular exclusion chromatography, which relies on selective permeation based strictly on molecular size. Let's actually look a bit closer at that third subdivision, molecular exclusion, which you might also hear called size-exclusion chromatography. If you think about the stationary phase particles, they aren't completely solid. They're actually filled with tiny pores. It acts precisely like a molecular sieve. As the mixture travels through, the really big molecules are totally excluded from the pores because, well, they're just too large to fit. The smaller molecules, however, are able to permeate into the pores, meaning they take a much longer, winding path through the stationary phase. The source material provides a fantastic, highly relatable way to remember this concept, the traffic analogy. If you compare molecules to vehicles and the pores to a city traffic network, it clicks perfectly. The big molecules are like huge transport trucks. They can't fit into the narrow, winding city streets, so they just take the highway bypass around the whole city and get to their destination incredibly fast. The small molecules, on the other hand, are like compact cars. They take the off-ramp, get into that porous network of tiny city streets, and get slowed way, way down. Because of this, the big molecules always exit the column first, and the small ones exit last. Okay, let's move to our final section, Section 5, reading the chromogram. The tangible output of all this theoretical chemistry is a two-dimensional diagram known as a chromatogram. Time, or elution volume, runs along the horizontal axis, and the detector's signal is plotted on the vertical axis. On a typical graph, you'll notice these visual peaks rising up from a flat line at the bottom. That flat line, that's the baseline, and it represents when no analyte is present. When a separation is successful, you get a series of distinct, well-resolved peaks returning to the baseline, with each peak representing a separated component of your original mixture. The absolute key metric we're looking for on that graph is the retention time, designated as TR. This is simply the time taken between the very moment of injection into the system and the absolute maximum point of the peak recorded on the chromatogram. And right here is where it becomes a wildly powerful quantitative tool. If the detector signal varies linearly with the concentration of your analyte, then the total area under that peak varies linearly too. By calculating the area under the peak, we can determine exactly how much of that specific compound was in the original mixture. So to get that highly exact quantitative measurement, scientists basically follow two steps. Step 1, they inject a known reference compound to establish exactly how sensitive the detector is to that specific species. Step 2, they use a device to calculate the exact mathematical area of the eluting peaks during the actual sample run. This completely proves that chromatography isn't just about separating a mixture, it's about precise, incredibly accurate measurement.
And that really brings our whole journey full circle. We can summarize this entire complex, foundational process by returning to this incredibly elegant definition from the text. Chromatography is the method by which a mixture is separated into its components as a result of the relative ability of each component to be flushed along or through a stationary phase by a mobile phase. It's just a beautiful dance of physics and chemistry.
So I'll leave you with this final thought. Now that you understand the mechanics of this invisible separation technology, ask yourself, how might this exact process be impacting the world around you right now? From ensuring the safety of the food you eat and the purity of the water you drink, to verifying the precise chemical composition of the medicine you take every day, chromatography really is the invisible guardian of modern life. Thank you so much for joining me to decode this incredible topic. Keep exploring, keep questioning, and I'll see you in the next explainer.